We have Professor Cvitanovic from the physics department at Georgia Tech. He's a theoretical physicist. He believes passionately in the unity of the exact sciences. And in his chaosbook.org, he's developing theoretical tools that apply equally to classical chaos, turbulence, cardiac dynamics, stochastic dynamics, and quantum theories. He has contributed to quantum field theory, the theory of exceptional Lie groups, and his nonlinear dynamics researches span a broad range of physical problems from renormalization in transition to chaos to periodic orbit theory of quantum system to dynamical theory of hydrodynamical turbulence. Cvitanovic is also known for his very reasonably priced webbooks on field theory, group theory, and chaos. And,
yours for a click.
Welcome, welcome. And he's going to talk about noise is your friend. Thank you.
So, especially in this building, there is lots of brute computation going on, and it's going on all over this campus and in much of the world where people care about fluid dynamics, field theory, astrophysics, weather, geophysics. The common thing is that equations are often relatively simple, but solutions are very hard to come by, and the most familiar example is weather prediction. You know that it's very hard to predict weather. And today I want to talk about something that took us a while to figure out, and the mechanics of it is, kind of ugly. You need to know about Fokker-Planck operators and all kinds of things. But the basic ideas are very simple, so I'll try to do this in a way which is equation-free. So we will forget Brutus for a while, even though computations have to be hard. And we'll try to sneak by with something simple and clever, which is inspired by quantum mechanics and so-called WKB methods in quantum mechanics. In quantum mechanics, it's known since 1920s that you do get important intuition about solutions of quantum mechanical problems from classical mechanics. And there is a mechanism of doing that. So this is a little bit in this spirit. It should be easier to understand because there's nothing mysterious. We'll just talk about ordinary classical systems with a little noise added. Then we all have intuition about noise. And it turns out, I used to not like noise because I found it annoying. But it turns out in this context, noise is your friend. It's very helpful. It makes things that are insanely hard. You learn that you don't need to do them at all, which is, what you would like to know as a lazy scientist. So this work is worked together with Domenico Lippolis, who was a graduate student here and did his thesis on this subject, and Jeffrey Henninger, who used to be an undergraduate here and now is a graduate student in Texas, and he did his senior thesis on this work. So the whole point of this talk is I will explain in very general terms kind of problems that we solve today in combination of having better computers, but much more important, having better ways of thinking about problems. It turns out that thinking saves enormous amount when it comes to computing. And I'll talk about one particular problem, which is very vaguely called problem of chaos or turbulence, where you have simple equations, but the long-term dynamics can be very complicated and very unstable. So even if you observe a state of the system at some point, it might be very hard to predict what happens next. So then in this kind of problems, you have to learn how to enumerate possible states. And it turns out that noise is your friend because it tells you that number of possible states is always finite, which is just great. In principle, in determinism, there is infinitely many. Then there'll be a technical part, but I'll keep it very simple because the basic idea is very simple. Basic idea is that errors add up, squares of errors add up to square of accumulated error. That's all there is to it. And why we need to know how to stop. This I'm just taking as an example of what one can see experimentally, but also do computationally. What you're looking at is the state of turbulent fluid in the pipe, measured experimentally. And what's being shown is one instant of the fluid. And red regions are where the fluid is twirling to the right in some way. And so it has streamwise vorticity of certain value. Blue where it twirls the other way. And there are many, many visualizations of fluids. There's just one. But this teaches you that, well, structures are very complicated. You can recognize them. There's something about the structure that's recognizable. And today, we can say what's recognizable because we can actually solve numerically for certain subset of problems in turbulence and more generally in extended spatial systems. We can find exact solutions, numerical exact solutions. And these exact solutions can then be used to classify what you see here. It turns out they're very expensive to compute. So it took us 3 years from starting to computing first solution. 3 people. And there's larger community now, maybe not very efficient, but it takes at least 6 months or a year to learn how to do some of this stuff. So it's not easy. So you would like to know, now that you can do it, you would like to know, when can you stop doing it? So what is the problem? To have a solution of a state, described state of fluid, not statistically or visually, but actually have a precise description, you need to specify velocity of fluid every place in some given volume. So you need 3 vector at every position. And in practice, you do this by various discretization methods, spectral codes, etc. So you end up with finite representations where you interpolate between some values you compute. And no matter what you do, you have to compute between 100 to 1 million computational degrees of freedom from any instant. And this is evolving in time. Pretty soon you have terabytes of data. And, do you really need terabytes? I mean, is there that much information in this stuff? And, clearly it can be that much information because you, with your naked eye, could recognize the turbulence state. You could say that so it has lots of structures. So what do? You do what science has always done. You combine curiosity with bad eyesight. Because if you focus, there's a wonderful Borges story on exactitude in science, which you should all read, in which there is a country which makes maps. They're the best people in making maps. And eventually they decide they'll make one-to-one map of their country. And at that point, civilization collapses because by the time you've gotten all the information into your description, you have no understanding at all what's going on. So the blindness is very important. And in this case, the blindness is kind of obvious. This is, in principle, every state needs infinite specification because, there's a packet of fluid moving every place at any instant of time. So this is infinite amount of information. You have to specify lots of functions which have lots of information. And, but we don't care about all that. We care about, to some accuracy. You have to coarse partition and make it finite in some way. And in this kind of problems, this is totally natural. Our measurement is noisy. Our computation is noisy. The setup is noisy. The pipe is not perfect. Environment is noisy. And it only makes sense to describe the state up to some kind of noise level. So how do you do that? If you are thinking in a very idealized way in dynamical systems, you say your system is described as a manifold, which is enumeration of all possible states. all possible twirls of a fluid in a liter of a fluid. And any point in that space is a snapshot, instantaneous snapshots of what's going on. But if you have a noise-limited state space, that means that you'll have some kind of grid. You'll have a cage, and you'll just say, I'm in this part of the cage, like, I'm in a grid of New York, and I'm on 42nd and 2nd or something. I will not specify this up to angstrom accuracy. I'll only do it up to a block. So that's kind of obvious. And the intuition that all of us have is rather simple. It says, well, think carefully about physical noise in your problem is. And that's very hard. You have to think carefully because, if you have lots of variables, some of them might be noisy, some of them might be noisy. It might depend on the state of system, how noisy it is, etc. But if I have a good description of the noise, then whenever you give me a point with infinite precision, saying, I'm at pi over 2 times pi to the square over 6, you'll compute it to 3 digits and you'll say, I'm in that box. So you will assign to every state a volume, and then you will say, if my noise is 1%, I'll divide my length in 100, and I'll only be able to resolve it to 100 points, and I'll just cover it with little balls, and that'll be a partition. And eventually, when I have too many points and they're too noisy, I will not be able to distinguish two because their noises will overlap, and I'll stop. So that seems very simple, and that's what most literature seems to do, at least in physics literature. They say the noise resolution is I impose external noise or some specification of precision, and I'm done. So that seems reasonable. It seems reasonable to just grid stuff and stick it on computer, make it uniform. And it turns out in dynamics it's totally wrong. It's fundamentally and totally wrong. It turns out in nonlinear dynamics, when you have flows which move in complicated ways through state space, the memory of the noise is extremely important. And that's the point of my talk. I'll give you a description how you actually compute the, both your memory in past and the future for any state in a space. And that turns out to be not at all some kind of uniform ball covering of your state space. Which, in retrospect, it sounds stupid anyhow because your coordinates were arbitrary, uniform balls, etc. It's totally wrong. But the result is actually quite beautiful. It turns out that once I tell you what problem I'm working on, what are my laws of motion, laws of nature that I'm describing. They could be gravitational, or they could be fluid dynamics, or they could be many other things. But they're deterministic, they're given. And noise or precision, etc. Then this machinery will produce a new version of the state space, which will be covered with cigars. And these cigars will sit only where the important stuff happens. So usually what happens in dynamics, you have infinite many degrees of freedom, but the motion is attracted to something called strange attractor, to some small subset. Now, small subset could be 1,000-dimensional. It doesn't lend itself necessarily, but we'll be able to cover it in a very non-uniform way, but we're able to compute everything and tell you this is the best possible thing you can do with this space. You can only see such and such motion in the space with such states, and that's it. So that's the talk. And the final product should be something that Francesco calls turbulence.zip. I give credit to you, but somebody had this idea that eventually I'll just give you a USB stick, and this USB stick will have a zip file, and that zip file will have all turbulent states of your pipe, or all unhealthy states of your heart, like spiral, chaos on your heart, all possible things. So again, setting is, we have our laws, we believe them. They give us predictions in deterministic sense. And we have a space of states. In it, we have representative point. Now, you have to understand the representative point is not like, this point in the 3 coordinates in this room. It could be a 1,000,000-dimensional vector space in which a point is this. So anytime I see video and anytime I film a chaotic trajectory, turbulent state, it'll just draw a line through this infinite dimensional space, which is trajectory, and that line is described by equations of motion. And if I take a neighborhood, then what my laws will do in time, they'll map neighborhood to another neighborhood. So, dynamical systems, deterministic ones, are specified by a pair saying, this is state space, all possible things that can exist. And this is the law that tells me what happens to those states. And each one of them has unique future, sometimes unique past. So how do dynamicists deal with this kind of problems? Well, let's say, look at these states, and this vortex looks like here there are 2 vortices, but when I looked at that snapshot, there are 4 vortices when I was looking at it. So let's partition the space in the things that look like 2 vortices and 4 vortices, and I'll make some coarse partitions. So here I've taken the only thing that I can draw, but this is, 1,000,000-dimensional state space, and I've divided it into 3 balls. Let's say if I'm here, I'll call this 0, 1, 2, or A, B, C, or something. And then I'll study what happens, and I'll discover that within my state of, 1 vortex state, a minute later, some of them have stayed 1 vortex, some initial conditions, others have gone someplace else and developed into 2 or 3 vortices. And that produces a systematic way of refining the partition. Or you can, make your computer just partition. And this is how you do it. But in dynamics, intelligent thing uses the past and the history of doing this. And this is great, except in deterministic dynamics, this can go on to infinitesimally small neighborhoods. This never stops. There's no reason why it should stop. So you enumerate states, and the finer your enumeration is, more of them you have, and that's it. But in practice, we should stop. So how do we stop when there is noise? In determinism, we said we could distinguish by some criterion, these kind of states from that one. There was a border between them. Now, if system is noisy, the border cannot be sharp because everything is a little bit noisy. So what used to be, a hypersurface that's subdivided state of my space states distinct regions, now it's something that's almost certainly this and almost certainly that. And then there's a fuzzy region in between because the wall has become a fuzzy wall whose width has to do with the noise or precision of the problem. Now you can see what's going to happen. As we keep subdividing it, for example, if you subdivide every region in 3, they'll get exponentially small because the volumes will roughly go like 3 to some power. But the walls don't get small. So pretty soon the walls will overlap, and it'll make no sense to subpartition states into distinct states because within our resolution we can't see the difference. So that has to stop. So that is a nice thing to do, but it turns out it's very hard to do because you have a big space, and maybe it's 100-dimensional. That it means that walls in it are 99-dimensional. They're 1 dimension less to separate it. And it's hard to, describe million-dimensional fuzzy surfaces, etc. But there is another thing we can do. One thing we've been able to do in deterministic systems, we've been able to find solutions which are called equilibria. These are solutions which don't move at all in time. So they're like, on top of the hill and you don't go on either side. Or periodic motions. So these are motions which, repeat. They do something complicated, but after a finite time, they repeat exactly and they repeat. And those things are very nice because they're points. They're lines, the periodic orbits are lines, and they describe points moving around them, no matter in how many dimensions you are. So if I can fuzz out that thing, that's much easier than fuzzing out a wall of huge dimensionality. So that's the first idea. Instead of dividing the world by fuzzy walls, we find recurrent trajectories, which are called periodic trajectories. So there's special conditions within each region that have property that they return to that region after finite time or finite number of steps if your dynamics is somehow discretized, etc. And now what we do is, if we can compute how fuzzed out, how fat is their neighborhood due to being kicked around by noise, then we'll start filling out the whole volume, because even though they're just a line, the fuzz will be the whole dimensionality of the space, because we can make noise in all dimensions. Typically, nothing can be infinitely precise. So we'll have, some kind of locally cigars or some kind of tubes. And as we try to stick more and more of these cigars into our world, eventually we won't be able to do, because they overlap. And once they overlap, there is no way of distinguishing whether I'm one or the other. Go to the airplane mode. Okay, so now how do we describe the neighborhood? So now I'll start the result, because lots of people in engineering actually know this result already. It's well known as a so-called Lyapunov equation. And here is what the result is, and then now I'll derive it. But and just in case you know it, you might, at this point, you might fall asleep. Suppose I have at time t, I've specified my state with some precision. And I'll assume that I'll always specify to Gaussian precision. It's the most natural thing to do. Now, Gaussian in many dimensions is described by covariance matrix. It's matrix which is symmetric and whose diagonals tell you how strong is noise in principal direction or singular directions of this thing. So that's what Q is. Then we have to describe how we kick our trajectory. And that's described again by covariance, because we usually assume that the kicking doesn't cause a drift, so that we, on the mean, kick equally often to the left and right. If it causes a drift, you can take care of it, so you can always go to frame where it doesn't. And that's described by the noise covariance matrix. And that's something you work very hard on, because that says that, I have a molecule moving and it can experience accelerations, but it's continuous, etc. So you describe that in great detail. And then from the dynamics, there's a thing I'll explain in a second called linearized flow. It says in a neighborhood or a flow, you can use a Jacobian matrix to describe how the neighboring points move with respect to you. That's described by this matrix M. And the whole thing says, I'll say it now and I'll say it 3 times, following Hilbert's dictum that you always have to say it 3 times when you're teaching a class. The noise at this time is the noise at previous time, 1 minute ago. My precision of my state 1 minute ago, but transported by the flow. And this sandwich here of Jacobians tells you how it gets distorted. You'll see this in a second. Then I added my kick, and that's a new covariance noise, because squares of errors add up as squares of errors, and that's all there is to it. But dynamics comes in through this Jacobian linearized flow. Now, the way we derive it, is the usual tedious thing about stochastic calculus. We have to describe some kind of Langevin flow. So that's a flow in which your increment is in part described by some deterministic velocity field, plus something that's called diffusion matrix, multiplying the standard Brownian noise. So that's called multiplicative noise, and that's the most standard way of describing how noise affects your systems if you don't make it colored, meaning having memory. And we assume that the noise is anisotropic, so it cares about whether you're changing momentum rather than position or something. It cares about what state you're in. The case where it's uniform is a special case, but you don't have to assume that. And multiplicative means it has this form here. And its strength is described by diffusion matrix, but in calculation, this becomes noise covariance matrix, which happens to be sigma t times sigma. So now that's about, now what we actually do is we go to Fokker-Planck formulation, because this describes one noisy trajectory, but you actually want to know about densities of trajectories. And that's described by Fokker-Planck equations, which are very pretty, and they look a little bit like Schrödinger equations of quantum mechanics. They are linear, and lots of time can be spent there, and lots of money can be made on the markets with this kind of thing. But the essence of it will be very simple. We'll assume that noise is weak, meaning the following thing, that there is a sensible period of time where your deterministic prediction is dominant feature of the flow. You're being fuzzed out, but for example, if you're looking at, we done this on neural cortex. So if you're looking at the hippocampus and looking at neuronal activity, if you find out that the noise caused by random fouling is larger than coherent motion that you can compute, then this is useless. You have to do something else. But if you find out that there is a significant, maybe 90% effect due in some short time, but time of interest, then this description might be useful to you. And that's what we mean by weak. Now, to illustrate the idea, I'll illustrate just on the simplest case, which was first done by Laplace, and for that reason it's called Ornstein-Uhlenbeck, who did it 150 years later. And everybody else did it. It's called harmonic oscillator for other people. I'll use one simple example to explain the equilibrium. It turns out that carries onto the general orbit. And the idea will be, I'll first tell you deterministic flow does this, then I kick it, and then I combine it, and that will be the description. So what does the deterministic flow typically do? Which you can do in any given trajectory. It's very natural to go into a co-moving frame, meaning that at any point as I move on trajectory, I measure distance to my neighbors relative to myself rather than in some arbitrary, external huge frame. So if I'm at point x n here, and I'm moving on a deterministic trajectory. Again, this is something that's embedded in any number of dimensions, but is given to us as a law of nature. Then the neighborhood, points in the neighborhood, which are a little bit away, they will get multiplied by this Jacobian length someplace else. And that will give me the new position of a neighbor time till later with respect to where I am at that time. And only thing we need to do is Jacobian. Now, it turns out that when we solve our difficult problems in fluid mechanics, we actually have to compute this Jacobian. So that's important for us because we already computed this quantity and we'll be using it to do noise. So it's not that I'm requiring something, criminally more difficult to do. You've already done part of the work just by the fact you have the trajectory. So now what happens to the covariance? Covariance is the average of, if I have a cloud of points, each point having coordinates z with respect to the origin where I am, then covariance matrix is the average over all these products of quadratic products of them. So that's what covariance matrix is. So this is just averaging our whole cloud of neighbors. Now what happens to this cloud of neighbor in one time step? What happens is that each neighbor gets multiplied by Jacobian, so it gets moved away by this linearized flow. But that's just the matrix of numbers, so that goes outside. And I find out that the covariance maps to the covariance sandwiched by these two Jacobians. And that's very natural because covariance is a bilinear thing. It's a second order thing I'm computing. So that's what determinism does. Now we add noise. And because covariance is that, the noise just says the new covariance is covariance at this time plus the kick. And I find that if I started with some ball of initial conditions, after one time in my time units, I'll find a cigar because it'll stretch in various ways. Stretching has to do both with dynamics not being isotropic. Dynamics never is for nonlinear problems. And the noise covariance matrix is never isotropic either, unless you're doing very simple textbook problem. So that's it. So that gives me this equation, and it has very simple interpretation. My cloud gets distorted, and then it gets smeared out a little bit, and this goes on. So this is what my cloud is at the next thing to the Gaussian accuracy. If you need more accuracy, then we need to do something else. So now this adds along the trajectory. And now you have to start thinking about, what happens to this as a long time, because I keep doing this. And there's a very simple case, which everybody understands intuitively. If my point that I started working was an attractive fixed point of the flow. Attractive point means that when I compute its stability, all of its eigenvalues are such, all of Jacobian eigenvalues are multiplied such that they're smaller than 1. So the neighborhood keeps getting shrunk into the point deterministically. But the noise doesn't like that because it keeps kicking it around. So obviously cannot go to the point. And now what happens is that when you look at this process, the original covariance gets off to the minus infinity, and you actually forget where you came from. So you get a natural measure which is totally uninterested where you started your thing. Your initial state was falling into this hole, but now you get a balance between being pulled in and kicked by randomness, and eventually you just get a balance between the two. You get a natural measure as example. So again, this equation comes from Lyapunov's doctoral dissertation. For different reasons, he was studying stability of solar system. It happens to the quadratic level. The Lyapunov function tends to be this thing that we are describing here. And here is a simplest example that anybody who teaches stochastic processes to you should teach you. And this is, and in our building you can see experiments, and other physicists from our department, other buildings do experiments, optical experiments. If you put a styrofoam ball into the biological fluid where there is lots of activity, it'll get kicked around. But if you use optical tweezers, you use harmonic force to keep it someplace, you'll find out that the ball just jerks around, but it doesn't go away too far because it's forbidden by harmonic attraction, but it can stay still because it's being kicked. And we'll attain a distribution like this, which turns out to be Gaussian. And it has a covariance which is proportional to the noise, but inversely proportional to this quantity instability. So if the contraction is very strong, then the natural measure will actually just be the noise itself, because contraction is so fast that you don't even see it. So you only see the noise. If contraction is very weak, so it's of order 1, almost 1, you'll find out very broad distribution, because the thing believes it can do random walk until it gets far enough to get pulled by harmonic oscillator back. So this is a totally sensible result, and it's very typical, and we use it a lot in various experiments, especially in biophysics today. Now, I'll give you a version of it. If you have this was done at a fixed point, but you might have a limit cycle. So in biology, very often you see situations where you get nonlinear clocks, where you get things that oscillate periodically, but they move very fast, and then they move very slow, and they move very fast, because they have some nonlinear law of motion. And the simplest example is a two-dimensional braccillator, which is one of the models that came from chemistry. So what that model has is that, depending on its parameter values, it might have an equilibrium point, its point here. But when it goes unstable, the way it goes unstable, that it creates a limit cycle. So you get periodic motion, and now what you can do is you can put a little cube, ellipsoid of noise, and just run it. So this is done, this is numerical simulation. And then there is a green thing, which is the analytic estimate. And what happens to it is, it goes, the noise increases, something happens, then suddenly it goes bananas. According to our estimate formula I gave you, the noise should be enormous. Things should be very fuzzy. Then it continues along and goes here. And it turns out here there's so much squeezing, because in that area there wasn't all that much pulling, but in this corner you really get shrunk in, and this whole noise gets compressed in a little corner, and bingo, it looks like the previous noise and just goes around. So this is an example of how these natural measures look like a nonlinear system. The world is not at all partitioned in equal balls. There's some areas which are huge, and other areas which are very small, and it only cares about dynamics, and the noise that we're giving here is the additive noise I described before, so it's not there's something weird about noise. It's just that balance of nonlinear dynamics says that partition of the space, really cares about dynamics. And so, no matter what you think, in nonlinear dynamics, there is always memory of noise, and it always does this, and it's always multiplicative, and it's never uniform, So that's easy to understand. Then, it turns out that what we care about nonlinear dynamics are not stable solutions. So, any textbook on stochastic calculus should be teaching you Ornstein-Uhlenbeck. They might call it something else. They might call it, Friedland, Wentzer, whatever. I mean, it has like 60 names because everybody does it at some point or later when they start thinking about noise. Of course, if you go from physics to chemistry to mathematics to engineering, it changes its name, but it's the same idea. It just basically the expression. But what's important to us, and it's also sometimes important in control engineering, is that we actually don't care only about stable things and how they get fuzzed out by noise. We very often care about unstable things. So the exact solutions that I referred to in fluid dynamics, they're exact, but they're all unstable. And the moment you have something unstable, it's not at all obvious how you take care of the noise, because unstable systems work like this. In the unstable direction, you have an error which is, millimeter is multiplied by 10, so it's centimeter by 10. So it goes exponentially. But your noise is always being added as 1 millimeter, you know. So you would think noise is irrelevant in expanding directions because it's a little thing and there's a huge instability. But, you know, that cannot be right. So what we did next is we looked at chaotic systems, such in which all orbits were unstable. And we figured out that there is also a law like that, but then instead of looking, you know, how you establish balance between contraction and being shoved around in the future, you have to look where you came from and how well can you hit the point I'm at now. You know, what's the neighborhood from which I can hit it? That's called adjoint Fokker-Planck or something, but you know, that's what it does. And if you repeat this thing, you get something that looks almost like the Lyapunov equation and is also known in control theory. But it has a different interpretation. So this says at this time, I came from someplace and you know, this thing was trying to destabilize me, but it destabilized just in such a way that the current covariance plus the noise equal that, as opposed to the other thing before where I was, you know, because when you have noisy system, you cannot go into the past. You can only go in the future because noise is irreversible. So that turned out to work pretty well. But then the systems that we really care are stable in some directions, like million directions, and unstable in others, like 20 directions. So the problems that we care about in many, you know, like turbulence, have a property that there's a finite number of directions in which things are unstable, and everybody else is just shoving us into these directions. So we have to figure out how to do that. And now a thing happens that drives me crazy. You know, I teach math method course. I explain why complex analysis is beautiful and Cauchy formula, you know, why I can take a Cauchy counter. But usually, I know the result I'm proving already is just a very elegant way of proving things to do with Green's functions, etc. In this case, actually, I don't know. You know, it turns out the complex magic works again, and I'm able, using it, so, or we are able as a collaboration, using it, we are able to deal simultaneously with the future and the past by separating the future and past. And you know, this is not at all obvious that they should be separable, because it could be, you know, if the noise comes in this way, contracting and something is going out that way, it's not obvious to me that some of the noise could not be transported out by the other eigenvalues. It turns out they can be separated. And we are able to assign to every state in the fluid, even in a case where I have a dynamics which is mixed, some stable, unstable, we can assign a cigar. Part of it describes the future, part of it describes the past. And I can cover everybody by this kind of cigars. So now the problem is solved. And you know, now we have kind of solved our main challenge. So the idea was, our question was, if you tell me what the noise is, what laws are, you know, how many distinct states can I enumerate? And when I'm done with description, now we claim that's done, because we can use the periodic points to partition the deterministic state space, and then we can associate to each one their cigars, and we can do this recursively by looking at longer and smaller neighborhoods, and we stop when they overlap, and we are done, and we go home. We have an optimal partition. So, and this is rather beautiful partition because it's intrinsic to the dynamics. And it's not a piece of mathematics in the sense that we can actually compute it. It's not that I just talk to you here, but we can actually go on a computer, and for given problem, we can actually compute this. Because what does it require? We have to solve deterministic problem, and we have to solve its stability. And that's it. If you know the Jacobian and deterministic problem, then it tells me how it massages the external noise to give me natural measure, the thing that forgets all about initial conditions. So the space that people would like to divide in little cubes is now divided in cigars. They're very non-uniform, and they have to be. And now, does it work? So, today we have hundreds of these things. We have Jacobians. It's very hard to get, but we got them. And we not know whether it works because we've only tested in few dimensional models, low dimensional models. So maybe this is all very unrealistic, but it's very pretty. So anybody wants to do this, step up after the talk. I will immediately try to be helpful. But the main message is that, now that we can do very hard problems, we might have a criterion also when to stop doing very hard stuff. When we can go home. We call it optimal partition hypothesis. I think it's the best of all possible. It's not mathematics, so everything I tell you might be wrong in some sense, but it's good for government work. So that's it. So anyway, so I know that it looks very abstract to you, but I decided to talk about this because you do hard problems. Many people who I recognize numerically. It might be helpful to know, what noise does to hard problems. And it's good. It's not bad.
Thank you.
So that delta N.
Yeah.
It's an excellent talk. Thank you very much
Thanks.
for the talk. I was thinking about the delta N, which is the covariance of the noise.
Yeah.
You assume to be stationary?
It's stationary. I forgot to say.
Stationary.
Yeah. It has to be stationary.
It's the same for the approach to work with Jacobians. But
Yeah. Both the velocity. Yeah.
I suspect that in many cases it depends on the dynamics itself, which means that there's a dynamical relationship of the noise.
Well, here I hope that we have accounted for it because the result, all the memory has been created by dynamics.
But the strength of the noise itself.
Yeah, we
Related to the dynamics as well.
we only related to the state of the system, but not to the dynamics. That would be called color noise. We would need to know some history, and that's also a real problem. But we claim that here the dynamics, the eventual noise is the one that includes the memory. So the Q that I compute is the.
So my next question was, so you're trying to through this approach to the focal plane equation to understand how the density of the state, probability density
Yeah.
of the state is going to turn around. And so there must be some threshold beyond which the whole thing becomes indistinguishable.
Yeah. I agree. I mean that's our criterion, right?
Yeah. So your work includes, for example, for a particular system with certain nonlinear dynamics. You can also give a criterion that says,
I mean, our criterion is where.
What noise is there beyond which we are really getting into some sort of.
Oh, when I change the noise itself.
Yeah.
Don't know because we are really using weak noise in this because we are using now the Brutus shows up in the first thing because to check it we actually solve Fokker-Planck numerically, which we can do in low dimensions. We can do in high dimensions. So, they compare well. The natural measure that we get pieced together from this neighborhood and the natural measure that we get just knowing nothing but solving numerically the Fokker-Planck. There's more granularity in our measure than in the real one. It's smoother, but it's pretty good.
Yeah. And my last question is of course, in reality, you don't know what the noise is.
That's where all the thinking goes in. Yeah.
Is it possible through this approach dynamics and how often, the points get repeated, and you keep the same profile, could you tell that, in a perfectly deterministic system, chaotic system, or semi-periodic system, you will come back to the same point? But isn't there a way to establish what is the area that is changing because of the noise that is there, which you don't know, and therefore create the boundaries for the ellipses that you're delineating?
I'm involved in a project that has to do with birdsong and experimentalist, and how well the bird learns the same song. They learn the same thing. So there are lots of trials, but we don't know the noise. Yeah. So we're trying to use, maybe this is answering your question, but by measuring the natural measure of our trials, because they all end up, all the birds, or the bird does reproduce the same song almost the same way, 400, 500. So you can do the statistics, and we can kind of perturb the song. So we can explore. We try to go backwards and find what's the neuronal network noise that's implicit in learning this thing. But I agree, it's an extremely difficult problem. So we don't have good examples. Yeah.
I hope the birds are not parrots, because that's very nonlinear.
No, all baby birds have to learn songs, and they're non-linear, but they're fixed points. I mean, they learn the same thing.
Thank you.
David.
Can anything be said about quantum correction?
Everybody can leave because graduate students have done their duty.
Can anything be said about quantum corrections?
Yeah, so that was a secret motivation behind this, because the stochastic processes are easier to deal with because we believe we have better intuition. They turned out to be technically quite difficult. So the answer is I don't know, but that was the motivation, to see whether I changed we have granularity. I mean, I wouldn't say it in this room, but you're a physicist, so I cannot say it. We have phase space has this h-bar granularity, and we believe it, etc. But effectively, maybe it's not the real granularity when you have dynamics. So that was because I'm thinking how to use this in quantum field theory while I'm doing Navier-Stokes, and there the h-bar shows up, and the classical equations are like the Navier-Stokes equations. So it's WKB approximation. But no, we are not able to do it. You can talk to Burak if he's around. Burak, are you here? He decided not to hear. But anyway, there's a graduate student who's going to do quantum field theory of this.
So this Cauchy magic.
Yeah.
So again, now I can see the equation. Now, if the matrix is not normal, you are claiming that you still get the separation, that the noise doesn't mix.
Yeah.
Can you see that things directly from your equation?
I don't recommend it. I mean, yeah. I mean, it's one of those crazy things. Linear algebra is trivial. The contour integrals are trivial. It's mind-boggling because you have to do similarity transformation, then you have to orthogonalize it, to do transpose something, etc. And then you have to follow somebody's theorem, and then you take the contour, and voila, the thing is separated.
It's kind of counterintuitive, right?
Well, it just worked, but maybe at some point we'll understand, because lots of things have gotten simpler, but this one I just find mind-boggling. I just didn't expect I would do a contour integral and something as simple as a linearized flow of, I mean, the problem is very simple.
But this is a short time, right? These things are all...
No, this is anytime.
Anytime. Even the Cauchy magic.
Yeah, no, it does it for arbitrary times.
Okay, another question?
And we learned it in control theory paper. They did it. It wasn't in physics. It was in someplace.
Other questions? Okay, I think thank you for coming, and